The solar system is an intricate and fascinating realm filled with planets, moons, asteroids, comets, and a central star that powers all activity within its borders, the Sun. Though it's just a small part of the vast cosmos, the solar system holds a special place in our understanding of space and our place within the universe. By examining the components of our solar system, we gain insight into the processes that have shaped not only our planetary neighborhood, but also the wider universe. This chapter will explore the solar system's overview, formation, and key celestial bodies, including asteroids, comets, and dwarf planets, providing a comprehensive look into our cosmic neighborhood. The solar system, often described as a miniature model of the universe, consists of the Sun, 8 major planets, their moons, and countless smaller celestial objects, such as asteroids, comets, and dwarf planets. The Sun, which accounts for more than 99.8% of the total mass of the solar system, lies at its center, providing the energy and gravitational force that holds everything together. The planets, which orbit the Sun, are divided into 2 main categories: the 4 inner terrestrial planets, Mercury, Venus, Earth, and Mars, and the 4 outer gas giants, Jupiter, Saturn, Uranus, and Neptune. The inner solar system is composed of the terrestrial planets, which are characterized by their rocky surfaces and relatively small size. These planets are closer to the Sun and have shorter orbital periods compared to the outer planets. Mercury is the closest planet to the Sun and also the smallest of the 8 planets in our solar system, with a diameter of about 4,180 kilometers, 3,032 miles. It has an orbital period of just 88 Earth days, meaning it completes a full orbit around the Sun in less than 3 months. Being so close to the Sun, Mercury experiences extreme temperature fluctuations. Daytime temperatures can soar to 427 degrees, 800 degrees Celsius, while nighttime temperatures plunge to 173 degrees Celsius, 280 degrees Celsius, because of its lack of a significant atmosphere to retain heat. Mercury's surface is heavily cratered and resembles Earth's moon, a testament to its long history of impacts from asteroids and comets. This cratered landscape gives Mercury its rugged, ancient appearance. Caloris Basin, one of the largest impact craters in the solar system, is found on Mercury, with a diameter of about 1,550 kilometers, 960 miles. Despite being so close to the Sun, Mercury has no natural satellites or moons, likely due to its proximity to the Sun's strong gravitational field, which may have prevented Mercury from capturing or retaining any moons. Venus is often called Earth's sister planet because of its similar size, mass, and composition. However, its surface conditions are drastically different from Earth's. Venus has a thick atmosphere, primarily made up of carbon dioxide, CO2, with clouds of sulfuric acid that obscure its surface from direct view. This dense atmosphere causes a runaway greenhouse effect, trapping heat and making Venus the hottest planet in the solar system, with surface temperatures reaching a scorching 462 degrees Celsius, 864 degrees Celsius, hot enough to melt lead. Venus rotates very slowly on its axis, taking about 243 Earth days to complete a single rotation. Moreover, Venus rotates in the opposite direction of most other planets, meaning that if you stood on Venus, the Sun would rise in the west and set in the east. The surface of Venus is volcanic and tectonically active, with vast lava plains, volcanic mountains, and plateaus. Maxwell Montes, the tallest mountain on Venus, reaches about 11 kilometers, 7 miles in height, which is comparable to Earth's tallest mountain, Mount Everest. However, because of Venus's thick atmosphere and intense pressure, about 92 times that of Earth's sea level, exploring its surface presents extreme challenges. There are no known natural satellites orbiting Venus. Earth is the 3rd planet from the Sun and the only planet known to support life. It is unique in the solar system for its combination of liquid water, a stable atmosphere, and a magnetic field, all of which are critical to sustaining life. Earth's atmosphere is composed primarily of nitrogen, 78%, and oxygen, 21%, with trace amounts of carbon dioxide, water vapor, and other gases. This balanced composition, along with the greenhouse effect, allows Earth to maintain temperatures that are conducive to life. Earth has a magnetic field generated by the movement of molten iron in its outer core, which protects the planet from harmful solar and cosmic radiation. This magnetic shield is essential for preserving Earth's atmosphere and protecting living organisms from dangerous particles. Earth's moon is also unique among the terrestrial planets. It is relatively large in comparison to Earth, and its gravitational pull influences tides and helps to stabilize Earth's axial tilt. This stabilization plays a critical role in maintaining Earth's relatively mild and predictable climate, which is important for the development and evolution of life. The surface of Earth is dynamic, with plate tectonics driving the movement of continents, the formation of mountains, and volcanic activity. The presence of vast oceans covering approximately 71% of Earth's surface is also a key feature that distinguishes Earth from other planets in the solar system. Mars, the fourth planet from the Sun, is often called the red planet due to the iron oxide, rust, that gives its surface a reddish hue. Mars has a diameter of 6,679 kilometers, 4,212 miles, making it about half the size of Earth. It has a thin atmosphere primarily composed of carbon dioxide, 95%, with nitrogen and argon making up most of the rest. This thin atmosphere provides little protection from cosmic and solar radiation, and it also contributes to the planet's cold temperatures, which can drop to as low as 125 degrees Celsius, 195 degrees Celsius, in winter. Mars is home to some of the most impressive geological features in the solar system. Olympus Mons, the tallest volcano in the solar system, stands at an astonishing 22 kilometers, 13.6 miles high, nearly 3 times the height of Mount Everest. Mars also has a vast canyon system known as Valles Marineris, which stretches for over 4,000 kilometers, 2,500 miles, and is up to 7 kilometers, 4.3 miles, deep. This makes it much larger and deeper than the Grand Canyon on Earth. Mars has been a focus of intense exploration, with multiple robotic missions searching for signs of past or present life. Evidence suggests that Mars once had liquid water on its surface, and there may still be subsurface water ice today. Mars has 2 small moons, Phobos and Deimos, which are likely captured asteroids. The outer solar system consists of the gas and ice giants, which are much larger than the terrestrial planets and have thick atmospheres composed mainly of hydrogen and helium. These planets are also known for their ring systems and numerous moons. Jupiter is the largest planet in the solar system, with a diameter of 142,984 kilometers, 88,846 miles, making it over 11 times wider than Earth. Jupiter is classified as a gas giant, primarily composed of hydrogen, about 90%, and helium, about 10%, much like the Sun. This immense planet lacks a solid surface. Instead, its atmosphere gradually transitions into denser layers of gas and liquid hydrogen as you go deeper. One of Jupiter's most iconic features is the Great Red Spot, a massive storm that has been raging for at least 350 years. This storm is so large that it could fit multiple Earths inside it, measuring approximately 16,350 kilometers, 10,159 miles in diameter. The exact cause of the red coloration is still a mystery, but it's believed to be due to chemical reactions in Jupiter's atmosphere, involving elements like phosphorus or sulfur. Jupiter has an incredibly strong magnetic field, about 20,000 times stronger than Earth's, which creates powerful radiation belts around the planet. This magnetic field traps charged particles from the Sun, producing intense radiation that can pose a danger to spacecraft. Jupiter also has an extensive family of moons, with more than 70 known moons. The largest and most notable are the Galilean moons, discovered by Galileo Galilei in 1610. Io, the most volcanically active body in the solar system, with hundreds of volcanoes spewing sulfur and other materials. Europa, a moon with a smooth, icy surface, beneath which scientists believe lies a vast subsurface ocean, making it one of the prime candidates for the search for extraterrestrial life. Ganymede, the largest moon in the solar system, even larger than Mercury. Ganymede has its own magnetic field, a feature unique among moons. Callisto, the most heavily cratered object in the solar system, with a surface that dates back to the solar system's early history. Jupiter's moons and its massive size, combined with its strong magnetic field, make it a complex and fascinating planet to study. Saturn, the second largest planet in the solar system, is another gas giant similar to Jupiter, composed primarily of hydrogen and helium. Its diameter is about 120,536 kilometers, 74,197 miles. And like Jupiter, it lacks a solid surface. Saturn's most distinct feature is its extensive and stunning ring system, which is the largest and most visible of any planet. Saturn's rings are composed of ice and rock particles, ranging in size from tiny dust grains to objects as large as small mountains. The rings are divided into several distinct sections, with the main rings labeled A, B, C, and so on. These rings are incredibly thin, only about 20 meters, 66 feet, thick, despite spanning hundreds of thousands of kilometers in diameter. Saturn's rings are believed to be remnants of a shattered moon or leftover material from the planet's formation. Saturn has 83 known moons, but the most fascinating is Titan, the largest of Saturn's moons. Titan is unique in the solar system because it has a thick atmosphere, primarily composed of nitrogen, and is the only moon known to have liquid lakes on its surface. However, these lakes are not composed of water, but of liquid methane and ethane. Titan's atmosphere and surface features make it a subject of great interest, especially for astrobiologists. The moon also has seasonal weather patterns, with methane rain forming rivers and lakes, much like water does on Earth. Other notable moons include Enceladus. This small moon is covered in ice, with water vapor plumes erupting from its south pole, indicating the presence of a subsurface ocean. Like Europa, Enceladus is considered a prime candidate for the search for life. Rhea and Dione. These are medium-sized moons that have heavily cratered surfaces and icy compositions. Uranus is an ice giant, differing from gas giants like Jupiter and Saturn due to its higher concentration of water, ammonia, and methane, in addition to hydrogen and helium. Uranus is about 50,524 kilometers, 31 t, 118 miles in diameter, making it the third largest planet in the solar system. It orbits the Sun at a distance of 2.87 billion kilometers, 1.78 billion miles. One of the most unusual features of Uranus is its axial tilt of about 98 degrees, which causes the planet to rotate on its side relative to the plane of the solar system. This extreme tilt results in bizarre seasonal variations. Each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness. This unique orientation is thought to be the result of a giant collision with an Earth-sized object early in the planet's history. Uranus has a faint ring system, consisting of dark, narrow rings that are difficult to observe from Earth. These rings are primarily composed of ice and dust particles. Uranus also has 27 known moons, with the largest ones being Titania, Oberon, Ariel, Umbriel, and Miranda. Miranda, in particular, stands out due to its strange, patchwork-like surface with giant canyons, cliffs, and ridges, indicating a complex geological history. The moons of Uranus are named after characters from the works of Shakespeare and Alexander Pope. Neptune is the outermost planet in the solar system and the second ice giant, similar in composition to Uranus. It has a diameter of 49,244 kilometers, 30,598 miles, and is known for its vivid blue color, which is caused by the presence of methane in its atmosphere, which absorbs red light and reflects blue. Neptune is home to the strongest winds in the solar system, with speeds that can reach 2,100 kilometers per hour, 1,300 miles per hour, or supersonic speeds. The planet's atmosphere features giant storms, much like Jupiter's Great Red Spot. One such storm, known as the Great Dark Spot, was observed by the Voyager 2 spacecraft in 1989, although it has since dissipated, suggesting that Neptune's storms are more short-lived than those on Jupiter. Neptune has a faint ring system composed of ice particles, dust, and possibly organic compounds. Unlike Saturn's well-defined rings, Neptune's rings are thinner and less complete, often described as arcs. Neptune also has 14 known moons, with the largest and most famous being Triton. Triton is unique because it orbits Neptune in the opposite direction, retrograde, of the planet's rotation, suggesting that it may have been a captured object from the Kuiper Belt. Triton has geysers that eject nitrogen gas from its surface, indicating that it may still be geologically active. Triton is also thought to have a subsurface ocean, raising the possibility of potential life beneath its icy surface. Beyond the orbit of Neptune lies the Kuiper Belt, a region filled with icy bodies and dwarf planets, including Pluto, once considered the 9th planet of the solar system, before being reclassified as a dwarf planet in 2006. The Kuiper Belt is similar to the asteroid belt, but far larger and more massive. It is the source of many short-period comets, and its objects are remnants from the early solar system. Further out, surrounding the solar system in a spherical shell, is the Oort cloud, which is believed to be the source of long-period comets. Though no direct observations of the Oort cloud have been made, its existence is inferred based on the behavior of comets. The solar system formed about 4.6 billion years ago from the gravitational collapse of a giant molecular cloud. This process, known as nebular hypothesis, describes how a cloud of gas and dust, called the solar nebula, collapsed under its own gravity to form the Sun and the planets. The solar nebula was composed mainly of hydrogen and helium, with trace amounts of heavier elements that had been created by previous generations of stars. As the nebula contracted, it began to spin faster, flattening into a rotating disk. The central region of this disk, where most of the material concentrated, became the protostar that would eventually ignite to form the Sun. As the protostar continued to accumulate mass from the surrounding nebula, the pressure and temperature at its core increased. Once the temperature reached about 10 million degrees Celsius, nuclear fusion began, and the Sun was born. The fusion process converts hydrogen into helium, releasing vast amounts of energy, which powers the Sun and gives it its radiant glow. As the Sun formed, the remaining material in the disk began to clump together due to gravity. In the inner part of the disk, where temperatures were higher, only metals and silicates could condense, leading to the formation of the terrestrial planets. In the outer regions, beyond the frost line, temperatures were cooler, allowing volatile compounds like water, methane, and ammonia to condense. This led to the formation of the gas giants, which could capture large amounts of hydrogen and helium from the nebula. The process of planet formation can be broken down into several key stages. 1. Dust and gas condensation. Tiny grains of dust and ice particles collided and stuck together, forming larger and larger clumps over time. 2. Planetesimals. These clumps eventually grew into kilometer-sized objects known as planetesimals. Their gravity allowed them to attract even more material, growing into larger bodies. 3. Protoplanets. As planetesimals collided and merged, they formed protoplanets, the precursors to planets. During this stage, the solar system was a chaotic place, with frequent collisions between growing protoplanets. 4. Clearing the neighborhood. The final stage of planet formation involved protoplanets clearing their orbits of smaller debris through gravitational interactions. This process took tens of millions of years and resulted in the formation of the 8 major planets we see today. While planets dominate the solar system, smaller celestial bodies like asteroids, comets, and dwarf planets also play significant roles. These objects are remnants from the early solar system, providing valuable insights into its formation and evolution. Asteroids are rocky objects that primarily reside in the asteroid belt, a region between the orbits of Mars and Jupiter. The largest of these, Ceres, is also classified as a dwarf planet. Asteroids are remnants from the solar system's formation that never coalesced into a planet, primarily due to the gravitational influence of Jupiter, which disrupted the accretion process. Asteroids vary greatly in size, composition, and shape. Some are composed of metal-rich materials, while others are primarily silicate or carbonaceous. The study of asteroids provides clues about the conditions of the early solar system, and they are of particular interest due to their potential for future mining operations. Comets are icy bodies that originate from 2 main regions of the solar system, the Kuiper Belt and the Oort cloud. When comets approach the Sun, the heat causes their icy nuclei to sublimate, releasing gas and dust that form a glowing coma and a characteristic tail. Short-period comets have orbits that take them close to the Sun every few decades or less, and they originate from the Kuiper Belt. Long-period comets, on the other hand, take thousands or even millions of years to complete their orbits, and they originate from the distant Oort cloud. Comets are often described as dirty snowballs because they are composed of a mix of ice, dust, and organic compounds. They are thought to be some of the most primitive objects in the solar system, preserving material that dates back to its formation. Dwarf planets are celestial bodies that share some characteristics with planets, but do not meet all the criteria to be classified as full-fledged planets. The most well-known dwarf planet is Pluto, which was reclassified in 2006 after the discovery of other similar-sized objects in the Kuiper Belt. To be classified as a dwarf planet, an object must 1. Orbit the Sun. 2. Be spherical in shape due to its own gravity. 3. Not have cleared its orbital path of other debris. In addition to Pluto, other recognized dwarf planets include Eris, Haumea, and Makemake, all of which reside in the Kuiper Belt, and Ceres, which is located in the asteroid belt. The Sun, a nearly perfect sphere of hot plasma, is the central star of the solar system, providing the gravitational force that keeps planets, moons, comets, and asteroids in orbit. Its energy, produced through nuclear fusion in its core, is responsible for the light and heat that make life on Earth possible. The Sun is not only essential for life, but also plays a critical role in the dynamics of the entire solar system. In this chapter, we explore how the Sun generates energy, its life cycle from birth to eventual death, and the effects of solar winds and magnetic activity on the planets. The Sun produces energy through the process of nuclear fusion, which occurs in its core. At the core, temperatures reach about 15 million degrees Celsius, 27 million degrees Fahrenheit, where hydrogen atoms are fused together to form helium. This process releases vast amounts of energy in the form of light and heat. The energy generated by the Sun radiates outward, first traveling through the radiative zone, then the convective zone, and eventually reaching the surface or photosphere, from which it is emitted into space. This energy is crucial for the solar system, particularly for Earth. Solar energy powers nearly all life on the planet by driving photosynthesis in plants, which forms the foundation of food chains. It also regulates the Earth's climate, creating weather systems and ocean currents. Without the Sun's energy, Earth would be a frozen, lifeless world. The Sun's massive gravitational pull, which accounts for 99.8% of the total mass of the solar system, holds the planets and other celestial objects in stable orbits. This gravitational force maintains the orbital paths of planets and shapes the overall structure of the solar system. It is the dominant force governing the motion of all objects in the solar system. The distance from the Sun plays a critical role in determining a planet's environment. The habitable zone, sometimes referred to as the Goldilocks zone, is the region around a star where conditions are just right for liquid water to exist on a planet's surface. Earth is located in this zone, allowing it to sustain life. Planets like Venus, which are closer to the Sun, experience extreme heat, while planets like Mars, located on the outer edge of the habitable zone, are much colder. The energy emitted by the Sun affects not only Earth, but all planets in the solar system. Planets closer to the Sun, such as Mercury and Venus, are subjected to intense solar radiation, while the gas giants like Jupiter and Saturn receive much less energy, resulting in colder environments. Solar radiation also influences planetary atmospheres. For example, Venus experiences a runaway greenhouse effect due to the thick carbon dioxide atmosphere trapping heat from the Sun. On Mars, the thin atmosphere provides little protection, leading to extreme temperature fluctuations between day and night. The Sun's energy also drives the formation of auroras on planets like Earth, Jupiter, and Saturn. These spectacular displays of light, known as auroras or northern and southern lights, occur when charged particles from the Sun interact with a planet's magnetic field and atmosphere. Like all stars, the Sun has a finite lifespan. It is currently about 4.6 billion years old, approximately halfway through its life. The Sun's life cycle can be divided into several stages, from its birth in a nebula to its eventual fate as a red giant and, ultimately, a white dwarf. The Sun was born out of a giant cloud of gas and dust, known as a nebula, about 4.6 billion years ago. This process began when a region of the nebula collapsed under its own gravity, forming a dense core known as a protostar. As the protostar continued to accumulate material, it became hotter and denser. Eventually, the temperature in the core became high enough to ignite nuclear fusion, marking the birth of the Sun. Currently, the Sun is in the main sequence phase of its life cycle, which is the longest and most stable period in the life of a star. During this phase, the Sun is fusing hydrogen into helium in its core, a process that releases energy and sustains the star. This phase will last for about 10 billion years in total, meaning the Sun has roughly 5 billion more years before it exhausts its hydrogen fuel. The balance between the outward pressure from the energy generated in the core and the inward pull of gravity keeps the Sun stable. This equilibrium ensures that the Sun's size and brightness remain relatively constant throughout this period. Once the Sun depletes its hydrogen supply, it will enter the next phase of its life cycle, the red giant phase. During this stage, the core will begin to collapse under gravity, while the outer layers expand significantly. The Sun will grow to many times its current size, possibly engulfing the inner planets, including Mercury, Venus, and even Earth. In the red giant phase, the core will heat up to the point where it can fuse helium into heavier elements such as carbon and oxygen. However, this stage will not last long compared to the main sequence phase, and the Sun will eventually shed its outer layers, forming a planetary nebula. After the red giant phase, the Sun's core will be left behind as a white dwarf, a small, dense remnant composed mostly of carbon and oxygen. White dwarfs no longer undergo fusion, and they slowly cool and fade over billions of years. This will be the final stage of the Sun's life cycle. While the Sun will never become a supernova, its fate as a white dwarf is a relatively peaceful end compared to more massive stars that end in catastrophic explosions. The Sun is a dynamic and active star, constantly emitting streams of charged particles known as solar winds. These winds are composed primarily of electrons and protons that escape the Sun's atmosphere and travel through the solar system at speeds of up to 900 kilometers per second. Solar winds have a profound effect on the solar system, particularly on the magnetospheres of planets. Solar winds affect planets in different ways, depending on their distance from the Sun and the strength of their magnetic fields. Earth's magnetosphere, for example, serves as a protective shield, deflecting the majority of the solar wind. Without this magnetic shield, Earth's atmosphere could be stripped away by solar winds, as has happened on Mars, which has a much weaker magnetic field. Solar winds also interact with the atmospheres of planets to create phenomena such as auroras. When charged particles from the solar wind collide with atoms in a planet's atmosphere, they release energy in the form of light, creating beautiful auroras near the poles of Earth, Jupiter, Saturn, and other planets with strong magnetic fields. Solar activity is not constant. It fluctuates over time in cycles known as solar cycles, which last about 11 years. During periods of high activity, the Sun produces solar flares and coronal mass ejections, CMEs, powerful bursts of radiation and charged particles. Solar flares are sudden bursts of energy from the Sun's surface, caused by the release of magnetic energy. These flares emit intense radiation, including X-rays and ultraviolet light, which can disrupt satellite communications and power grids on Earth. Coronal mass ejections, CMEs, are massive clouds of solar plasma ejected from the Sun's corona. When CMEs reach Earth, they can interact with the planet's magnetosphere, causing geomagnetic storms. These storms can lead to auroras, but also pose risks to satellites, astronauts, and power infrastructure on Earth. The Sun's magnetic field is highly complex and dynamic. It is generated by the movement of plasma within the Sun's interior, which creates electric currents. The magnetic field is not uniform. It varies in strength and shape over time. One of the most visible manifestations of the Sun's magnetic activity is the appearance of sunspots, which are cooler regions on the Sun's surface caused by intense magnetic activity. The Sun's magnetic field also influences the solar wind and space weather, affecting conditions throughout the solar system. Changes in the Sun's magnetic activity can have significant impacts on space weather and technological systems on Earth, making the study of the Sun's magnetism crucial for both understanding solar dynamics and protecting our technological infrastructure. The planets of the solar system, each unique in its composition, size, and atmospheric dynamics, form a diverse family of celestial bodies orbiting the Sun. From the small, rocky terrestrial planets closest to the Sun, to the massive, gaseous, and icy giants in the outer regions of the solar system, these worlds offer fascinating insights into planetary formation, evolution, and the conditions that might support life. Additionally, the moons that orbit these planets, particularly Europa, Titan, and Ganymede, add to the complexity and diversity of the solar system. This chapter delves into the characteristics of the terrestrial planets, the gas and ice giants, and the most intriguing moons of the solar system. The four inner planets of the solar system, Mercury, Venus, Earth, and Mars, are known as the terrestrial planets. These planets are composed primarily of silicate rocks or metals, and their surfaces are solid. They are much smaller than the outer planets and have relatively high densities. Each terrestrial planet has a unique atmosphere, geology, and climate, making them diverse worlds of study. Mercury, the smallest planet in the solar system and the closest to the Sun, experiences extreme conditions due to its proximity to the star. With an average distance of about 58 million kilometers, 36 million miles from the Sun, Mercury has a highly elliptical orbit, and it completes a full revolution around the Sun in just 88 Earth days. One of the most striking features of Mercury is its lack of a substantial atmosphere. The planet's thin exosphere, composed of trace amounts of oxygen, sodium, hydrogen, helium, and potassium, cannot retain heat. As a result, Surface temperatures on Mercury vary dramatically, from scorching highs of about 430 degrees Celsius, 800 degrees Fahrenheit, during the day, to frigid lows of 180 degrees Celsius, 290 degrees Fahrenheit, at night. Mercury's surface is heavily cratered, similar to Earth's moon, a result of numerous collisions with asteroids and comets over billions of years. The planet has virtually no weathering or erosion processes due to its lack of atmosphere, preserving its ancient landscape. Caloris Basin, one of the largest impact craters in the solar system, spans about 1,550 kilometers, 960 miles across, highlighting the violent history of impacts that shaped the planet. Despite its small size, Mercury has a disproportionately large iron core, which generates a magnetic field about 1% as strong as Earth's. This magnetic field interacts with the solar wind, creating a dynamic and complex magnetosphere. Mercury's lack of moons and thin exosphere contribute to its status as a unique and enigmatic world. Venus, the second planet from the Sun, is often referred to as Earth's sister planet due to its similar size, mass, and composition. However, Venus has an atmosphere and climate that are drastically different from those of Earth, making it one of the most inhospitable places in the solar system. Venus is covered by a thick atmosphere composed mainly of carbon dioxide, 96.5%, with traces of nitrogen and sulfuric acid clouds. This dense atmosphere creates an extreme greenhouse effect, trapping heat and raising the planet's surface temperature to an average of about 465 degrees Celsius, 870 degrees Fahrenheit, hot enough to melt lead. As a result, Venus is the hottest planet in the solar system, even hotter than Mercury, despite being farther from the Sun. Venus has a day length of 243 Earth days, which is longer than its year of 225 Earth days. Additionally, Venus rotates in the opposite direction of most planets, a phenomenon known as retrograde rotation. This means that on Venus, the Sun rises in the west and sets in the east. The surface of Venus is dominated by vast volcanic plains, with evidence of both ancient and active volcanic activity. Maxwell Montes, the highest mountain on Venus, rises 11 kilometers, 7 miles above the surface. The planet is also home to Ishtar Terra and Aphrodite Terra, large highland regions that cover a significant portion of the planet. Despite its extreme surface conditions, Venus has been the subject of intense study due to its similarities with Earth and the potential clues it may offer about climate change and planetary evolution. Understanding how Venus evolved into such a hostile environment helps scientists better understand the delicate balance that allows Earth to sustain life. Earth, the third planet from the Sun, is unique in the solar system as the only known planet to support life. Its ability to harbor life is due to a combination of factors, including its distance from the Sun, its protective atmosphere, the presence of liquid water, and a magnetic field that shields the planet from harmful solar radiation. Earth is the largest of the terrestrial planets, with a diameter of about 12,142 kilometers, 7,218 miles. Its surface is 71% covered by water, which is essential for life. The planet's atmosphere, composed mainly of nitrogen, 78%, and oxygen, 21%, plays a critical role in regulating temperature, weather, and the water cycle. Earth's geology is highly dynamic, with tectonic plates constantly shifting and reshaping the surface. This movement leads to the formation of mountains, earthquakes, and volcanic activity, all of which have influenced the evolution of life. Earth's magnetic field, generated by the movement of molten iron in its outer core, extends far into space and protects the planet from the solar wind. The Moon, Earth's only natural satellite, plays a significant role in stabilizing the planet's axial tilt, which helps moderate the climate and create the seasons. The Moon also influences tides, which are vital for coastal ecosystems and human maritime activities. Mars, the fourth planet from the Sun, is often referred to as the Red Planet due to the iron oxide, rust, that gives its surface a reddish appearance. Mars has been the focus of numerous space missions in the search for past or present life, as it shares some similarities with Earth, including polar ice caps, seasonal changes, and a day length of about 24.6 hours. Mars has a thin atmosphere composed mainly of carbon dioxide, 95.3%, with traces of nitrogen, argon, and oxygen. Because its atmosphere is so thin, Mars experiences extreme temperature fluctuations, with daytime highs reaching up to 20 degrees Celsius, 68 degrees Fahrenheit, and nighttime lows dropping to 73 degrees Celsius, 100 degrees Fahrenheit. The surface of Mars is marked by vast plains, towering volcanoes, and deep canyons. Olympus Mons, the largest volcano in the solar system, stands at 22 kilometers, 13.6 miles high, and Valles Marineris, a canyon system that stretches over 4,000 kilometers, 2,500 miles, dwarfs Earth's Grand Canyon. Mars is also home to two small, irregularly shaped moons, Phobos and Deimos, which are thought to be captured asteroids from the nearby asteroid belt. Scientists believe that liquid water may have once flowed on the surface of Mars, as evidenced by dried-up riverbeds, valleys, and sedimentary rock formations. The presence of subsurface water and seasonal methane emissions has fueled speculation that microbial life may still exist on Mars today. The four outer planets, Jupiter, Saturn, Uranus, and Neptune, are vastly different from the terrestrial planets in both composition and size. These planets are known as the gas giants, Jupiter and Saturn, and ice giants, Uranus and Neptune. They are characterized by their thick atmospheres, low densities, and large numbers of moons. Jupiter, the largest planet in the solar system, is a gas giant composed primarily of hydrogen, about 90%, and helium, about 10%, similar to the composition of the Sun. With a diameter of 139,820 kilometers, 86,881 miles, Jupiter could fit more than 1,300 Earths inside its volume. Its massive size gives it a powerful gravitational influence, which has helped shape the solar system. Jupiter's atmosphere is a swirling mass of clouds and storms, with bands of clouds moving in opposite directions due to strong jet streams. The most famous of these storms is the Great Red Spot, a giant storm that has been raging for at least 400 years. The storm is large enough to fit 2 or 3 Earths inside. Jupiter radiates more heat than it receives from the Sun due to gravitational compression and heat from its formation. The planet has a strong magnetic field, which is about 20,000 times more powerful than Earth's. This magnetic field creates intense radiation belts around the planet. Jupiter has at least 79 moons, with the 4 largest, Io, Europa, Ganymede, and Callisto, known as the Galilean moons, discovered by Galileo Galilei in 1610. These moons are some of the most fascinating objects in the solar system and are explored in more detail later in this chapter. Saturn, the second largest planet in the solar system, is best known for its extensive ring system, which is composed of billions of particles ranging in size from tiny grains to large boulders. These rings are made primarily of ice and rock, and are thought to be remnants of comets, asteroids, or shattered moons. Saturn is composed mainly of hydrogen, about 96%, and helium, about 3%, with traces of methane, ammonia, and other gases. The planet has a diameter of about 116,460 kilometers, 72,366 miles, and, like Jupiter, radiates more energy than it receives from the Sun. This excess energy is thought to come from helium rain, where helium droplets condense and fall into the planet's core, releasing heat. Saturn's atmosphere is less turbulent than Jupiter's, but it still has powerful storms, including the mysterious hexagonal storm at the planet's north pole. Saturn also has a strong magnetic field, though weaker than Jupiter's, and it influences the planet's many moons and ring system. Saturn has at least 83 moons, with Titan being the largest and the only moon in the solar system with a thick atmosphere. Titan's surface is rich in methane and ethane lakes and rivers, making it one of the most intriguing places in the search for extraterrestrial life. Uranus, the seventh planet from the Sun, is unique among the planets because of its extreme axial tilt of 98 degrees. This means that Uranus essentially rolls around the Sun on its side, leading to extreme seasonal changes. Each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness. Uranus is classified as an ice giant due to the presence of water, ammonia, and methane ices in its composition, in addition to hydrogen and helium. Its atmosphere is primarily hydrogen, about 82%, helium, about 15%, and methane, about 2.5%, which gives the planet its blue-green color. The methane absorbs red light, leaving only the blue-green wavelengths to be reflected back to observers. Uranus has a diameter of about 50,724 kilometers, 31,518 miles, and is the coldest planet in the solar system, with minimum temperatures reaching 224 degrees Celsius, 371 degrees Fahrenheit. The planet has a faint ring system and at least 27 known moons, with Miranda being one of the most geologically active and deformed moons in the solar system. Neptune, the eighth and farthest planet from the Sun, is similar to Uranus in its composition as an ice giant. Neptune has a diameter of about 49,244 kilometers, 30,598 miles, and is composed primarily of hydrogen, 80%, and helium, 19%, with traces of methane, about 1%, giving it a vivid blue color. Neptune's atmosphere is known for its supersonic winds, the fastest in the solar system, which can reach speeds of up to 2,400 kilometers per hour, 1,500 miles per hour. The planet is home to large storms, including the Great Dark Spot, similar to Jupiter's Great Red Spot, though the Great Dark Spot has disappeared and reappeared over time. Neptune has 14 known moons, with Triton being the largest. Triton is unique in that it orbits Neptune in the opposite direction of the planet's rotation, a phenomenon known as retrograde orbit. This suggests that Triton may have been captured by Neptune's gravity rather than forming alongside the planet. In addition to the planets, the solar system is home to more than 200 moons, each with its own unique characteristics. Some moons are geologically active, while others are frozen worlds. Among the most intriguing are Europa, Titan, and Ganymede, all of which have been the focus of scientific exploration due to their potential to harbor life or their unusual features. Europa, one of Jupiter's Galilean moons, is a world of particular interest to scientists because of the possibility that it harbors a subsurface ocean beneath its icy crust. Europa's surface is covered by a layer of water ice, with cracks and ridges that suggest the presence of a liquid ocean below. Europa is about 3,100 kilometers, 1,940 miles, in diameter, slightly smaller than Earth's moon. The most compelling evidence for an ocean beneath Europa's ice comes from observations of plumes of water vapor erupting from the moon's surface, suggesting that the ocean may be interacting with the surface through cracks in the ice. This subsurface ocean could contain more water than all of Earth's oceans combined and may have the necessary conditions to support life. The interaction between the ocean and Europa's rocky mantle could create hydrothermal vents, similar to those found on Earth's ocean floors, which are known to support ecosystems. Titan, Saturn's largest moon, is unique in the solar system due to its thick atmosphere and the presence of liquid methane and ethane lakes on its surface. Titan's atmosphere is composed mainly of nitrogen, about 98%, with methane making up the rest. The atmospheric pressure on Titan is about 1.5 times that of Earth's, making it the only moon in the solar system with a substantial atmosphere. Titan's surface is incredibly cold, with temperatures averaging 179 degrees Celsius, 290 degrees Fahrenheit. Despite this, liquid methane and ethane can exist in lakes, rivers, and seas on the moon's surface. Kraken Mare, the largest sea on Titan, is filled with liquid methane and ethane, and it covers an area larger than the Caspian Sea on Earth. The thick atmosphere and surface liquids make Titan one of the most Earth-like bodies in the solar system. Titan's hydrological cycle, in which methane evaporates, forms clouds, and falls as rain, mirrors the water cycle on Earth. These unique characteristics make Titan a prime candidate for future exploration, particularly in the search for life. Ganymede, another one of Jupiter's Galilean moons, is the largest moon in the solar system, with a diameter of 5,268 kilometers, 3,273 miles, making it even larger than the planet Mercury. Ganymede is unique because it is the only moon known to have a magnetic field, likely generated by a liquid iron or iron sulfide core. Ganymede's surface is a mix of two types of terrain: dark, heavily cratered regions that are thought to be older, and lighter regions with grooves and ridges that indicate tectonic activity. The moon is believed to have a subsurface ocean, similar to Europa, though buried much deeper beneath the icy crust. Scientists are particularly interested in Ganymede's magnetic field and potential ocean, as they may provide clues about the moon's internal structure and its potential to support life. The JUICE mission, Jupiter Icy Moons Explorer, is set to launch in the 2020s and will study Ganymede, along with Europa and Callisto, to learn more about these intriguing moons. Earth, the third planet from the Sun, stands out as the only known planet in the universe to harbor life. Its unique combination of atmosphere, magnetic field, and geological activity creates a stable environment that supports a diverse range of ecosystems. However, Earth's place in the cosmos is not only defined by its ability to sustain life, but also by the profound influence of its natural satellite, the Moon, and the insights it provides into planetary science as a whole. In this chapter, we will explore Earth's distinctive features, the crucial role of the Moon, and how Earth's geology serves as a reference point for understanding other planets. The planet Earth is distinct in many ways, particularly in its combination of factors that allow for a stable environment conducive to life. These factors include the planet's protective atmosphere, its dynamic geology, and its powerful magnetic field, which together create a planet that has evolved to support billions of living organisms over billions of years. Earth's atmosphere, a protective shield. Earth's atmosphere is a critical component of what makes the planet habitable, composed mainly of nitrogen, 78%, and oxygen, 21%, with trace amounts of carbon dioxide, water vapor, and other gases. The atmosphere plays several key roles. 1. Protection from solar radiation. The atmosphere blocks harmful ultraviolet, UV, radiation from the sun, thanks to the ozone layer in the stratosphere, which absorbs the majority of the sun's UV rays. Without this protective layer, life on Earth would be subject to dangerous levels of radiation that could damage DNA and other biological molecules. 2. Temperature regulation. The atmosphere moderates the planet's temperature through the greenhouse effect, trapping heat to maintain a stable climate. While carbon dioxide and methane are present in small amounts, they are essential for preventing Earth from becoming too cold. Without these greenhouse gases, Earth's average temperature would be about 18 degrees, 0 degrees, well below freezing, making life as we know it impossible. 3. Weather and climate. The atmosphere is responsible for the planet's weather and climate systems. The interaction between solar energy, the Earth's rotation, and the planet's surface generates wind, clouds, rain, and storms. These systems distribute heat and moisture across the globe, supporting the diverse ecosystems that thrive on Earth. 4. Breathable air. Earth's atmosphere provides the oxygen necessary for the respiration of most life forms. Plants, through photosynthesis, convert carbon dioxide into oxygen, maintaining the balance of gases needed for animals and other organisms to survive. Another key feature that sets Earth apart from other planets is its magnetic field. Generated by the movement of molten iron in Earth's outer core, this magnetic field extends far into space and forms the magnetosphere, which shields the planet from harmful cosmic rays and solar wind. The solar wind is a stream of charged particles emitted by the sun. Without the magnetic field, these particles would strip away Earth's atmosphere over time, as is believed to have happened on Mars. The magnetosphere deflects most of these particles, creating a protective bubble around the planet. During periods of intense solar activity, such as solar flares and coronal mass ejections, CMEs, Earth's magnetic field plays an even more critical role. These powerful solar events can send vast amounts of energy and charged particles toward Earth. The magnetic field channels these particles toward the poles, creating stunning auroras, northern and southern lights, while preventing more serious disruptions to the atmosphere and surface. Earth's geological activity is another defining feature. Unlike most other planets, Earth's surface is constantly being reshaped by plate tectonics, a process that involves the movement of large plates that make up the planet's crust. This movement drives the formation of mountains, earthquakes, and volcanic activity, all of which play crucial roles in shaping the planet's surface and creating habitats for life. 1. Plate tectonics. Earth's crust is divided into several major and minor tectonic plates that float on the semi-fluid mantle below. These plates move due to convection currents in the mantle, leading to the formation of mountain ranges, ocean basins, and other geological features. When plates collide, they can push up mountain ranges like the Himalayas, while at mid-ocean ridges, new crust is created as plates move apart. The movement of plates also results in earthquakes and volcanic eruptions, which release energy from the Earth's interior and recycle elements vital to life, such as carbon. 2. Volcanism. Volcanic activity has played a significant role in shaping Earth's atmosphere and surface. Volcanoes release gases like carbon dioxide, water vapor, and sulfur dioxide into the atmosphere, which helps regulate the planet's climate over geological time. Volcanic eruptions also contribute to the formation of fertile soils, which support the growth of plants and the development of complex ecosystems. 3. Erosion and weathering. Earth's surface is continuously shaped by the forces of erosion and weathering. Wind, water, and ice wear down mountains, form valleys, and deposit sediments in rivers and oceans. These processes are part of Earth's natural cycles, helping to regulate climate and ecosystems over time. Earth's natural satellite, the Moon, plays a vital role in maintaining the stability of the planet's environment. Though it is much smaller than Earth, the Moon exerts a gravitational pull that has profound effects on the planet, influencing everything from the tides to the length of the day, and even the stability of the climate. The most noticeable effect of the Moon's gravitational pull on Earth is the tides. As the Moon orbits Earth, its gravity causes the oceans to bulge out in the direction of the Moon. On the opposite side of the planet, another bulge occurs due to the inertia of the water as Earth spins. These tidal bulges create the high and low tides that coastal areas experience each day. The tidal forces exerted by the Moon play a critical role in the movement of ocean currents, which help regulate Earth's climate by distributing heat around the planet. The mixing of ocean water driven by tides also affects marine ecosystems, influencing the distribution of nutrients and supporting diverse marine life. Additionally, the interaction between Earth's rotation and the Moon's gravitational pull is gradually slowing the planet's rotation. As a result, the length of Earth's day is increasing by about 1.7 milliseconds per century. This slowing of Earth's rotation is accompanied by a gradual increase in the distance between the Earth and the Moon, as the Moon moves away from the planet at a rate of about 3.8 centimeters, 1.5 inches, per year. Another crucial effect of the Moon is its role in stabilizing Earth's axial tilt, which is responsible for the planet's seasons. Earth's axial tilt is currently about 23.5 degrees, But without the moon's stabilizing influence, this tilt could vary dramatically over time. Without the moon, gravitational interactions with the sun and other planets could cause Earth's axial tilt to shift chaotically, leading to extreme changes in climate. A more pronounced axial tilt could result in severe seasonal variations, while a reduced tilt could lead to a lack of seasons altogether. By stabilizing the axial tilt, the moon helps maintain a relatively mild and predictable climate on Earth, which has been essential for the development of complex life. The moon's gravitational influence on Earth is not static. As mentioned earlier, the moon is slowly moving away from Earth, a process that will continue for millions of years. As the moon moves farther from the planet, its gravitational pull on Earth will weaken, leading to a gradual reduction in the strength of tides. In the distant future, this could have significant consequences for Earth's oceans and climate. Weaker tides may slow down ocean currents, which play a vital role in regulating climate. Additionally, the lengthening of Earth's day will continue, though these changes will occur over such long timescales that they will not be noticeable within human lifetimes. Earth, as the only known planet with life, serves as an essential model for understanding other planets, both in our solar system and beyond. By studying Earth's geology, atmosphere, and climate, scientists can draw comparisons with other planets to gain insights into their potential for habitability and the processes that shape them. Mars is perhaps the most studied planet in relation to Earth. Though much smaller and colder, Mars shares several similarities with Earth, including evidence of ancient river valleys, polar ice caps, and a day length similar to Earth's. By studying geological features on Mars, such as dried-up riverbeds and sedimentary rock layers, scientists can infer that liquid water once existed on the planet's surface, possibly for millions of years. Earth's history provides a framework for understanding how planets evolve over time. For example, Mars may have had a thick atmosphere and liquid water billions of years ago, but it lost most of its atmosphere, possibly due to the absence of a magnetic field to protect it from the solar wind. This understanding helps scientists assess the likelihood of life having existed on Mars in the past and guides the search for signs of ancient microbial life on the planet. Venus, often referred to as Earth's sister planet, offers a stark contrast to our planet's livable conditions. Despite being similar in size and composition to Earth, Venus is a hostile world with surface temperatures hot enough to melt lead and a thick atmosphere filled with carbon dioxide and sulfuric acid clouds. The extreme greenhouse effect on Venus provides a cautionary example of what could happen if a planet's climate becomes unbalanced. Studying Venus helps scientists understand the runaway greenhouse effect and its implications for climate change on Earth. Venus's geological history and current conditions serve as a reminder of how delicate the balance of factors is that make Earth habitable. In recent decades, the discovery of exoplanets, planets orbiting stars outside our solar system, has opened up new avenues of exploration in the search for life beyond Earth. Many of these exoplanets are located in the habitable zone of their parent stars, where conditions could allow for liquid water to exist. Scientists use Earth as a model to assess the potential habitability of these distant worlds. Factors such as atmospheric composition, surface temperature, and the presence of water are crucial in determining whether an exoplanet could support life. Earth's history, from its early molten state to the development of a stable climate, provides valuable insights into the processes that may occur on exoplanets. The study of Earth's unique characteristics also helps scientists identify biosignatures, or signs of life, that could be detected on exoplanets. For example, the presence of oxygen in an exoplanet's atmosphere, combined with other indicators like methane and water vapor, could suggest the existence of biological processes similar to those on Earth. The exploration of the solar system has been one of humanity's greatest achievements, allowing us to extend our reach far beyond Earth. From the early days of space exploration to the present, spacecraft, landers, and rovers have visited planets, moons, and other celestial bodies, revealing extraordinary details about our solar system. These missions have provided answers to fundamental questions about the nature of our cosmic neighborhood, while raising new ones about the potential for life and the future of exploration. This chapter examines the pioneering space missions, the groundbreaking discoveries on planets and moons, and the ambitious plans for the future of solar system exploration. Space exploration began in the mid-20th century, with the launch of the first artificial satellites and human spaceflights. As technology advanced, robotic spacecraft were sent to explore distant planets and moons, providing unprecedented insights into the solar system. Some of the most iconic and groundbreaking missions include Voyager, Cassini, and the Mars rovers. The Voyager missions, launched by NASA in 1977, are among the most famous and successful space missions in history. Voyager 1 and Voyager 2 were initially designed to explore the outer planets, but they have continued to send back data from the outer reaches of the solar system and beyond, making them humanity's farthest-reaching spacecraft. Voyager 1. After its launch in 1977, Voyager 1 conducted flybys of Jupiter and Saturn, sending back stunning images and data about the planets and their moons. In 1990, Voyager 1 famously captured the pale blue dot image of Earth from a distance of about 6 billion kilometers, 3.7 billion miles. In 2012, Voyager 1 became the first human-made object to enter interstellar space, crossing the boundary known as the heliopause, where the sun's influence ends and the interstellar medium begins. Voyager 2. Launched shortly after Voyager 1, Voyager 2 conducted flybys of Jupiter, Saturn, Uranus, and Neptune, becoming the only spacecraft to have visited the latter two planets. Voyager 2's flybys revealed the dynamic atmospheres of the gas and ice giants and discovered new moons and ring systems around these planets. In 2018, Voyager 2 also crossed into interstellar space, following in the path of its twin. The Voyager missions revolutionized our understanding of the outer planets, their moons, and the broader structure of the solar system. Their longevity and continued transmission of data decades after their launch remain a testament to the durability of the spacecraft and the importance of robotic exploration. The Cassini-Huygens mission, launched in 1997, was a joint project between NASA, the European Space Agency, ESA, and the Italian Space Agency, ASI. Its primary goal was to study Saturn and its moons, and it became one of the most successful planetary missions in history. Cassini Orbiter. Cassini entered orbit around Saturn in 2004 and spent 13 years exploring the planet, its rings, and its moons. The spacecraft captured stunning images of Saturn's ring system, revealing intricate details about the composition and structure of the rings. Cassini also conducted multiple flybys of Saturn's moons, including Titan and Enceladus, two of the most intriguing objects in the solar system. Huygens. Probe. In 2005, the Huygens probe, which was carried aboard Cassini, descended through Titan's thick atmosphere and landed on its surface. It was the first time a spacecraft had landed on a body in the outer solar system. Huygens sent back detailed images and data from Titan's surface, providing valuable information about the moon's methane lakes, rivers, and dense atmosphere. One of Cassini's most significant discoveries was the detection of water vapor plumes erupting from the surface of Enceladus, suggesting the presence of a subsurface ocean. This finding made Enceladus a prime target in the search for extraterrestrial life. Cassini also revealed the complexity of Titan's surface and atmosphere, with its liquid methane and ethane lakes, further increasing interest in this enigmatic moon. Cassini's mission ended in 2017 with a dramatic plunge into Saturn's atmosphere, a maneuver designed to prevent the spacecraft from potentially contaminating Saturn's moons. The Cassini-Huygens mission transformed our understanding of Saturn and its moons, and set a high standard for future planetary exploration. Mars has long been a target of exploration due to its proximity to Earth and the tantalizing possibility that it once harbored liquid water and possibly life. NASA has sent several successful missions to Mars, including a series of robotic rovers that have explored the planet's surface in unprecedented detail. Spirit and Opportunity. Launched in 2003, the Spirit and Opportunity rovers were designed to explore Mars's surface and search for evidence of past water activity. Both rovers vastly outlasted their expected lifespans, with Opportunity remaining operational until 2018. Their findings included signs of ancient water flows, such as the discovery of minerals that form in the presence of water and the detection of ancient lake beds. Curiosity. The Curiosity rover, which landed on Mars in 2012, continues to explore the Gale crater. Curiosity has provided a wealth of information about Mars's climate, geology, and the potential for habitability. One of Curiosity's key discoveries was the detection of organic molecules in Martian rocks, indicating that the building blocks of life may have existed on Mars in the past. Curiosity also found evidence of ancient lakes and rivers, further supporting the idea that Mars was once a much wetter planet. Perseverance. Launched in 2020, the Perseverance rover is the most advanced rover ever sent to Mars. Its mission is to search for signs of ancient microbial life and to collect samples for future return to Earth. Perseverance is exploring the Jezero crater, a region thought to have once contained a lake. In addition to its scientific instruments, Perseverance is carrying the Ingenuity helicopter, which has successfully conducted the first powered flights on another planet. The Mars rover missions have provided crucial data about the planet's past and present environment, helping to answer fundamental questions about whether Mars once supported life and whether it could be habitable in the future. Space missions have not only focused on the planets themselves, but have also targeted moons and other celestial bodies within the solar system. The exploration of moons like Europa, Titan, and Enceladus has opened up exciting possibilities in the search for life beyond Earth. Mars remains a primary focus of planetary exploration due to its similarities to Earth and the potential that it may have once supported life. Over the years, various missions have uncovered strong evidence of liquid water in Mars's past, with signs of ancient river valleys, lake beds, and minerals that only form in the presence of water. The Curiosity and Perseverance rovers continue to provide data on Mars's ancient climate and surface conditions, as well as clues about the planet's habitability. One of the key discoveries on Mars is the detection of seasonal methane emissions, which could indicate geological or even biological activity beneath the planet's surface. The presence of recurring slope lineae, RSL, dark streaks that appear to flow down Martian slopes during the warmer months, has further intrigued scientists, suggesting that liquid water may still exist on Mars in a briny form. Europa, one of Jupiter's Galilean moons, is a prime candidate in the search for extraterrestrial life due to the possibility that it harbors a subsurface ocean beneath its icy crust. Data from the Galileo spacecraft and other missions have revealed that Europa's surface is composed of a thick layer of ice, with cracks and ridges that suggest the presence of a liquid ocean below. Europa's subsurface ocean is thought to contain more water than all of Earth's oceans combined, and it may be in contact with the Moon's rocky mantle, creating the potential for hydrothermal vents similar to those found on Earth's ocean floors. These vents could provide the energy needed to support microbial life, even in the absence of sunlight. The upcoming Europa Clipper mission, set to launch in the 2020s, will conduct detailed flybys of Europa to investigate its potential habitability. The mission will focus on studying Europa's ice shell, subsurface ocean, and any potential signs of life. Titan, Saturn's largest moon, is one of the most Earth-like worlds in the solar system, with a thick atmosphere and a cycle of liquid methane and ethane similar to Earth's water cycle. Titan's surface features lakes, rivers, and seas of liquid methane, and its dense nitrogen atmosphere makes it the only moon in the solar system with a substantial atmosphere. The Cassini-Huygens mission revealed that Titan's surface is shaped by methane rain and seasonal changes, much like Earth's hydrological cycle. Titan's lakes and seas are concentrated around the polar regions, and the presence of sand dunes made of hydrocarbon particles suggests that winds are actively reshaping the landscape. The potential for life on Titan remains a topic of intense interest. While Titan's surface is too cold for liquid water to exist, some scientists speculate that life could exist in methane-based forms, or that liquid water may exist beneath the moon's icy crust. NASA's upcoming Dragonfly mission, set to launch in the mid-2020s, will send a rotorcraft to explore Titan's surface. Dragonfly will investigate the moon's prebiotic chemistry, atmospheric processes, and surface conditions, and search for signs of life. Another of Saturn's moons, Enceladus, has emerged as a top candidate in the search for life due to the discovery of water vapor plumes erupting from its surface. These plumes, first detected by the Cassini spacecraft, are thought to originate from a subsurface ocean beneath the moon's icy shell. Enceladus is relatively small, with a diameter of about 500 kilometers, 310 miles. But the presence of a liquid water ocean, along with evidence of organic molecules in the plumes, suggests that the moon may harbor the conditions necessary for life. The discovery of hydrothermal activity on the ocean floor, inferred from the presence of silica particles in the plumes, further supports the idea that Enceladus could be habitable. Future missions to Enceladus may focus on sampling the plumes directly to search for signs of life, or studying the moon's ocean in greater detail. The exploration of the solar system is far from over. With the advent of new technologies and growing international collaboration, the next decades will see an unprecedented era of exploration, including missions to Mars, the outer planets, and beyond. Upcoming missions aim to address some of the most fundamental questions about the origin of life, the formation of the solar system, and humanity's place in the cosmos. One of the most anticipated future missions is the Mars Sample Return Mission, a joint effort between NASA and the European Space Agency, ESA. The Perseverance rover is currently collecting samples from Mars's surface, which will be cached for later retrieval by a follow-up mission. These samples will be returned to Earth for detailed analysis, providing critical insights into Mars's past climate and potential habitability. In addition to robotic exploration, human missions to Mars are also on the horizon. NASA's Artemis program, which aims to return humans to the moon by the mid-2020s, is seen as a stepping stone to sending astronauts to Mars in the 2030s. These missions will pave the way for future human exploration of the Red Planet, with the goal of establishing a sustainable presence on Mars. Europa continues to be a high-priority target for future exploration due to its potential for harboring life. The Europa Clipper mission, set to launch in the mid-2020s, will conduct detailed flybys of Europa to study its ice shell, subsurface ocean, and geological activity. The mission will help determine the thickness of the ice and assess the habitability of the ocean beneath. In parallel, ESA's Jupiter Icy Moons Explorer, JUICE, mission will explore Ganymede, Europa, and Callisto, focusing on the potential for subsurface oceans and the icy moon's interactions with Jupiter's magnetosphere. JUICE is expected to launch in 2023 and arrive at Jupiter in 2031. Titan's complex chemistry and Earth-like processes make it a prime target for future exploration. NASA's Dragonfly mission, a rotorcraft designed to explore Titan's surface, will launch in 2027 and is expected to arrive in the mid-2030s. Dragonfly will investigate Titan's methane lakes, organic-rich dunes, and potential prebiotic chemistry, with the goal of understanding the moon's habitability. The outer planets, particularly Uranus and Neptune, remain largely unexplored compared to other parts of the solar system. Future missions may focus on sending orbiters or flybys to these ice giants to study their atmospheres, magnetic fields, and moons in greater detail. NASA and other space agencies are also considering missions to explore the Kuiper Belt and Oort cloud, the distant regions of the solar system where icy bodies and comets reside. These missions would provide valuable insights into the formation and evolution of the solar system. The Milky Way is the galaxy that houses our solar system and hundreds of billions of other stars, star systems, nebulae, and planets. As a barred spiral galaxy, it spans about 100,000 light-years in diameter and contains a complex structure of stars, gas, dust, and dark matter. Understanding the structure and key components of the Milky Way allows us to comprehend where our solar system resides within the galaxy and the forces that shape it. Central to the dynamics of our galaxy is the supermassive black hole Sagittarius A, which lies at the core of the Milky Way. This chapter delves into the structure of the Milky Way, our solar system's position within the galaxy, and the role of black holes in shaping our galactic home. The Milky Way is a vast and complex structure, classified as a barred spiral galaxy due to its spiral arms and central bar-shaped region. Its structure is composed of several key components: the spiral arms, the galactic core, and the dark matter halo. Each of these elements contributes to the formation and movement of stars and other celestial bodies within the galaxy. The Milky Way's most visually striking feature is its spiral arms, which form a pinwheel-like pattern extending outward from the galactic center. These arms contain a high concentration of young, hot stars, as well as clouds of gas and dust where new stars are actively forming. The spiral structure is created by the differential rotation of the galaxy. Stars and gas closer to the center of the Milky Way rotate faster than those farther out. The Milky Way has several spiral arms, with 4 major arms dominating its structure: the Perseus arm, the Sagittarius arm, the Scutum Centaurus arm, and the outer arm. In addition to these large arms, there are several minor arms and spurs that contain smaller concentrations of stars and gas. The spiral arms are regions of high star formation activity, and they play a crucial role in the evolution of the galaxy. Perseus arm. One of the largest and most prominent arms, the Perseus arm is home to many bright, massive stars and star-forming regions. Sagittarius arm. This arm is closer to the galactic center and is rich in star-forming regions, nebulae, and star clusters. Scutum Centaurus arm. Extending from the central bar of the galaxy, this arm is one of the most massive and densely packed regions of the Milky Way. Outer arm. The most distant major spiral arm, the outer arm contains fewer stars than the inner arms, but it is still an active region of star formation. These spiral arms are not static structures. They move and evolve over time as stars, gas, and dust are pulled into them by gravitational forces. As stars age and evolve, they migrate from the spiral arms into the galactic disk, where older stars reside. At the center of the Milky Way lies the galactic core or galactic bulge, a densely packed region of stars, gas, and dust. The core is home to millions of stars, including many old red giants, as well as the galaxy's supermassive black hole, Sagittarius A. The core is a complex and dynamic environment, with high-energy processes occurring due to the presence of Sagittarius A. Intense radiation and powerful gravitational forces influence the movement of stars and gas within the core, creating a region of high activity. The stars in the core are primarily older, metal-rich stars, though some new star formation occurs in the dense molecular clouds that are found near the center. The galactic core is surrounded by a central bar structure, which extends out into the inner spiral arms. This bar acts as a mechanism for transporting gas and dust from the outer parts of the galaxy into the core, fueling the supermassive black hole and triggering star formation. One of the most mysterious and elusive components of the Milky Way is its dark matter halo. While dark matter cannot be directly observed, its gravitational effects on the galaxy are evident. The halo is thought to extend far beyond the visible edges of the Milky Way, encompassing the entire galaxy and providing the extra mass needed to explain the observed rotational speeds of stars and gas in the outer regions of the galaxy. Without dark matter, the outer regions of the Milky Way would rotate much more slowly than they do, according to the visible mass of stars and gas. However, the presence of a dark matter halo provides the additional gravitational pull that keeps the galaxy's structure intact. Scientists estimate that dark matter accounts for approximately 85% of the total mass of the Milky Way, although its exact nature remains unknown. The dark matter halo also plays a role in the formation and evolution of galaxies. It is believed that dark matter clumps together to form gravitational wells, which attract normal matter, baryonic matter, and initiate the formation of stars, galaxies, and galaxy clusters. In this way, dark matter shapes the large-scale structure of the universe and the dynamics of galaxies like the Milky Way. The solar system is located in one of the Milky Way's spiral arms, specifically within a minor arm known as the Orion Cygnus arm, or local spur, which is situated between the larger Perseus and Sagittarius arms. Our solar system is about 27,000 light-years away from the galactic center, placing it within the galactic disk, the flat, rotating plane where most of the galaxy's stars, including the Sun, reside. The Orion Cygnus arm is a relatively small and less densely populated arm compared to the major spiral arms. Despite its size, it contains a variety of stellar objects, including star-forming regions, nebulae, and young star clusters. The Orion Nebula, one of the most famous star-forming regions in the galaxy, is located in this arm, as well as several other nebulae and molecular clouds where new stars are being born. The solar system's location in the Orion Cygnus arm provides a relatively stable and calm environment compared to regions closer to the galactic core or the more densely packed spiral arms. This stability may have been crucial for the development of life on Earth, as the solar system has been spared from many of the potentially catastrophic events, such as supernovae, that occur more frequently in other parts of the galaxy. Like all stars and planetary systems in the Milky Way, the solar system is constantly moving through space. The Sun, along with its planets, orbits the galactic center at an average speed of about 828,000 kilometers per hour, 514,000 miles per hour. It takes the solar system approximately 230 million years to complete one full orbit around the Milky Way's core, a period known as a galactic year. During its journey through the galaxy, the solar system passes through different regions of space, including the spiral arms, molecular clouds, and the interstellar medium. These movements can have significant effects on the solar system, including changes in the cosmic ray flux and encounters with nearby stars. However, the solar system's current position in the Orion Cygnus arm is relatively isolated, providing a stable environment for life on Earth. The Sun's orbit around the galactic center is not perfectly circular, but rather elliptical, and it is also tilted relative to the galactic plane. The solar system oscillates above and below the galactic plane as it moves through the galaxy, with each oscillation taking about 60 million years to complete. Some scientists have suggested that these oscillations may be linked to mass extinction events on Earth, as the solar system's passage through more densely populated regions of the galaxy could increase the likelihood of encounters with supernovae or other disruptive cosmic events. The Sun is currently located about 16 to 20 light-years above the galactic plane, and it is moving toward the plane at a speed of about 7 kilometers per second, 4.3 miles per second. In about 30 million years, the solar system will cross the galactic plane once again. though such crossings are unlikely to have immediate or dramatic effects on the solar system. Black holes are among the most enigmatic and powerful objects in the universe, and they play a central role in shaping the dynamics of galaxies. At the center of the Milky Way lies a supermassive black hole known as Sagittarius ADS, which has a mass equivalent to about 4 million suns. While black holes cannot be directly observed, their gravitational influence is evident in the motions of stars and gas in the galactic core. Sagittarius AD, SGR, ARG, is located in the heart of the Milky Way's core, in a region known as the central bulge. Despite its enormous mass, SGR ARGS is relatively quiet compared to the supermassive black holes found in some other galaxies, which are actively accreting large amounts of matter and emitting powerful jets of energy. In the case of SI, the black hole is currently in a quiescent state, with only small amounts of gas and dust being drawn into its event horizon. The presence of Sagittarius AD was confirmed through observations of the orbits of stars near the galactic center. These stars, known as S-stars, move in highly elliptical orbits at incredibly high speeds, indicating the presence of a massive, invisible object exerting a strong gravitational force. In 2002, the star S2 was observed passing extremely close to SGR AG, reaching speeds of up to 7,650 kilometers per second, 4,750 miles per second, as it swung around the black hole. This provided conclusive evidence of a supermassive black hole at the center of the Milky Way. Supermassive black holes like Sagittarius AD play a crucial role in the formation and evolution of galaxies. While the exact relationship between black holes and their host galaxies is not fully understood, it is clear that black holes influence the movement of stars, gas, and dust within galaxies. The gravitational pull of a supermassive black hole helps anchor stars and other material in the central regions of a galaxy, and the energy released by accreting black holes can regulate star formation by heating up or expelling gas. In some galaxies, active supermassive black holes generate powerful jets of energy that extend far beyond the galaxy's core. These jets can shape the structure of galaxies by influencing the distribution of gas and dust, suppressing or triggering star formation. While Sagittarius AD is not currently active, it may have gone through periods of intense activity in the past, and it could become active again in the future if it encounters a large cloud of gas or a passing star. The relationship between supermassive black holes and their host galaxies is a topic of ongoing research. One hypothesis is that galaxies and their central black holes grow together over time, with the mass of the black hole being proportional to the mass of the galaxy's central bulge. This correlation suggests that black holes and galaxies co-evolve, influencing each other's growth and development. Black holes also play a role in the broader cosmic structure. Mergers between galaxies, which are common in the universe, can lead to the merging of their central black holes. These mergers generate gravitational waves, ripples in space-time that can be detected by observatories like LIGO and Virgo. Studying these gravitational waves provides valuable insights into the formation and evolution of black holes and galaxies. Galaxies, the vast collections of stars, gas, dust, and dark matter, are the building blocks of the universe. Beyond the Milky Way lie countless other galaxies, each with its own unique characteristics and evolutionary history. Galaxies come in various shapes and sizes, from the elegant spirals to the smooth ellipticals and the chaotic irregulars. They are not isolated entities, but often exist in clusters and superclusters, forming the large-scale structure of the universe. The nearest major galaxy to the Milky Way, the Andromeda Galaxy, is on a collision course with our own galaxy, setting the stage for a dramatic galactic merger in the distant future. In this chapter, we will explore the types of galaxies, the large-scale structure of the universe, and the fate of the Milky Way and Andromeda. Galaxies are categorized based on their shapes and structures into three main types: spiral galaxies, elliptical galaxies, and irregular galaxies. Each type of galaxy has distinct features that reflect its formation and evolutionary history. Spiral galaxies, such as the Milky Way, are among the most visually striking and recognizable types of galaxies. They are characterized by their spiral arms, which extend outward from a central bulge. These arms contain large amounts of gas and dust, and they are regions of active star formation, where new stars are born in dense molecular clouds. Spiral galaxies have a disk-like structure, with a flat, rotating plane of stars, gas, and dust surrounding a more spherical bulge in the center. The central bulge often contains older, redder stars, while the spiral arms are home to younger, hotter stars. In addition to the visible stars and gas, spiral galaxies are also embedded in a dark matter halo, which provides additional mass and influences the rotation of the galaxy. Spiral galaxies are further divided into subcategories based on the tightness of their spiral arms and the size of their central bulge. These categories, known as SE, SB, and SEC, reflect a progression from tightly wound arms and large bulges, SA, to loosely wound arms and smaller bulges, SC. SA galaxies. These have tightly wound spiral arms and a prominent central bulge. They contain less gas and dust than later types and have slower rates of star formation. SB galaxies. These are intermediate between SA and SC galaxies, with moderately wound arms and a noticeable but smaller bulge. SC galaxies. These have loosely wound spiral arms and a small central bulge. They are rich in gas and dust and have high rates of star formation. Some spiral galaxies also have a bar structure extending through the central bulge, and these are known as barred spiral galaxies. The Milky Way is an example of a barred spiral galaxy. Bars are thought to form through gravitational interactions and play a role in funneling gas toward the center of the galaxy, fueling star formation and the growth of the central black hole. Elliptical galaxies have a very different appearance from spiral galaxies. They are spherical or elliptical in shape, with a smooth, featureless appearance and little or no visible structure. Unlike spiral galaxies, elliptical galaxies do not have spiral arms or a disk-like structure. Elliptical galaxies are composed mostly of older stars and contain very little gas and dust, meaning that star formation in these galaxies is minimal or non-existent. The stars in elliptical galaxies typically have random orbits, unlike the organized rotation seen in spiral galaxies. Elliptical galaxies range in size from giant ellipticals, which are among the most massive galaxies in the universe, to dwarf ellipticals, which are much smaller and fainter. Giant ellipticals are often found at the centers of galaxy clusters, where they may have formed through the mergers of smaller galaxies. These mergers result in the chaotic stellar motions and lack of star formation that characterize elliptical galaxies. The Hubble classification scheme divides elliptical galaxies into categories based on their elongation, with E0 representing nearly spherical galaxies and E7 representing the most elongated ellipticals. Irregular galaxies do not fit neatly into the categories of spiral or elliptical galaxies. As their name suggests, irregular galaxies have no defined shape or structure, appearing as chaotic collections of stars, gas, and dust. They often contain large amounts of gas and dust, making them sites of active star formation. There are two main types of irregular galaxies. 1. Type Wine irregulars, IRR-I. These galaxies are generally rich in gas and have regions of active star formation, but they lack the organized structure of spirals or ellipticals. An example of an IRR-I galaxy is the Large Magellanic Cloud, LMC, a satellite galaxy of the Milky Way. distorted by interactions or collisions with other galaxies. They often appear fragmented, with no obvious central core or organized pattern. Irregular galaxies are thought to form through gravitational interactions or collisions with other galaxies. These interactions can disrupt the structure of a galaxy, stripping away stars and gas and leaving behind a chaotic, irregular remnant. Galaxies are not isolated entities. They are often found in groups, clusters, and even larger superclusters. These structures are part of the large-scale structure of the universe, which is organized into a vast cosmic web of interconnected galaxies, clusters, and voids. A galaxy cluster is a group of hundreds to thousands of galaxies bound together by gravity. Clusters are among the largest gravitationally bound structures in the universe, with typical sizes ranging from a few million to several hundred million light-years across. The Virgo cluster, for example, contains more than 1,000 galaxies and is located about 54 million light-years from Earth. Galaxy clusters contain not only galaxies, but also large amounts of hot gas and dark matter. The hot gas, which is composed of ionized hydrogen and helium, emits X-rays, making galaxy clusters visible in X-ray wavelengths. Dark matter, which makes up the majority of the mass in clusters, can be detected through its gravitational effects on the motions of galaxies and the bending of light, known as gravitational lensing. Galaxy clusters are dynamic environments, with galaxies interacting and sometimes merging with each other. These interactions can trigger bursts of star formation or result in the stripping of gas from galaxies, quenching star formation. Over time, smaller galaxies can merge to form giant ellipticals, which often reside at the centers of clusters. Galaxy clusters themselves are often part of even larger structures known as superclusters. A supercluster is a collection of galaxy clusters and smaller groups of galaxies bound together by gravity. Superclusters are among the largest known structures in the universe, stretching across hundreds of millions of light-years. The Laniakea supercluster, which includes the Virgo cluster and the Local group, the group of galaxies that includes the Milky Way and Andromeda, is one of the largest known superclusters. It spans more than 500 million light-years and contains about 100,000 galaxies. The center of the Laniakea supercluster is a massive structure known as the Great Attractor, a region of space that exerts a strong gravitational pull on nearby galaxies, including the Milky Way. Superclusters are not evenly distributed throughout the universe, but are instead part of the cosmic web, a vast network of galaxies and clusters separated by enormous voids, regions of space where very few galaxies are found. This large-scale structure of the universe is the result of gravitational collapse over billions of years, as matter clumped together to form galaxies, clusters, and superclusters. The Andromeda Galaxy, M31, is the closest major galaxy to the Milky Way, located about 2.5 million light-years away. Andromeda is a spiral galaxy, similar in structure to the Milky Way, with a bright central bulge, sweeping spiral arms, and a dark matter halo. It is the largest galaxy in the Local group, which also includes the Milky Way, the Triangulum Galaxy, and several smaller satellite galaxies. Andromeda contains about 1 trillion stars, making it more massive than the Milky Way, which has an estimated 200 to 400 billion stars. The galaxy's spiral arms are home to numerous star-forming regions, nebulae and star clusters, similar to those found in the Milky Way. One of the most dramatic events predicted for the future of the Milky Way is its eventual collision with the Andromeda Galaxy. This collision is expected to occur in about 4.5 billion years, as the two galaxies are currently moving toward each other at a speed of about 110 kilometers per second, 68 miles per second. While the thought of two galaxies colliding may sound catastrophic, it's important to note that the vast distances between individual stars mean that direct collisions between stars are unlikely. Instead, the gravitational interaction between the two galaxies will result in the merging of their structures, with stars and gas being pulled into new orbits. As the Milky Way and Andromeda merge, their spiral structures will be disrupted, and they will form a single, massive elliptical galaxy. This new galaxy, sometimes referred to as Milkomeda, will contain the stars, gas, and dark matter from both galaxies. The merger will also likely trigger new bursts of star formation, as clouds of gas are compressed and heated by the gravitational forces. During the merger, the supermassive black holes at the centers of the Milky Way and Andromeda are expected to merge as well, creating an even more massive black hole. This process will release vast amounts of energy in the form of gravitational waves, ripples in spacetime that can be detected by observatories like LIGO and Virgo. In addition to its spiral arms and central bulge, the Andromeda Galaxy is surrounded by a number of satellite galaxies, smaller galaxies that orbit the larger galaxy. Some of these satellites include the Andromeda I, Andromeda Cetu, and Andromeda Third dwarf galaxies, as well as larger companions like the Triangulum Galaxy, M33. These satellite galaxies are gravitationally bound to Andromeda and will likely be involved in the future merger with the Milky Way. The interaction between Andromeda and its satellites, as well as with the Milky Way, provides valuable insights into the dynamics of galaxy mergers and the role of satellite galaxies in the evolution of larger galaxies.